Okay, in this video I'm going to look at systems of equations, which we've already looked at, but I'm going to look at how it relates to matrices. And so to start with, I'm just going to set about solving this system of equations using techniques that we're already familiar with. So I'll look at the variables here, and I think I'm going to eliminate the x. So eliminate the x. Now, if you're already confident with the steps, you can zoom ahead. I'm going to take equation 2, 2x minus y plus z is 5. And I combine it with equation 1, so I want two lots of equation 1 is going to be 2x minus 6y plus 4z is equal to 4. And to eliminate the x's from these, I'm going to subtract. So I'm going to get 2x minus 2x disappears, that's what I'm trying to do. Minus 1 minus minus 6 is 5y. Z minus 4z is minus 3z. 5 minus 4 is 1. Okay, so I've got x eliminated from there. I'm now going to eliminate x from another pair of equations. Let's do 2 and 3. So, okay, I'm going to do equation 2. 2x minus y plus z is 5. Equation 3, 2x plus y plus 4z is minus 3. I'm going to subtract these. I'm going to go, what am I going to do? I'm going to go 2x minus 2x is 0. I'm going to go y minus minus y is 2y. 4z minus z is 3z, and I've gone bottom minus top, so I need to do minus 3 minus 5 is minus 8. Call that equation 5. Then I need to eliminate either the y or the z from 4 and 5, and I can see that the z coefficients match nicely. So if I go equation 4 is 5y minus 3z is 1, and equation 5 is 2y plus 3z is equal to minus 8. Then, of course, I can now add these together to get 7y is equal to minus 7, and then y is equal to minus 1. So I've got one of the variables out. At that point, I can then go back to either 4 and 5 and find z, and at that point I can go back to any of the original equations to find x. And if you want to follow that through for yourself, you can do so, and just check that you then follow z with minus 2 and x with 3 are the solutions to that system of equations. Okay, now I'm going to solve the same problem again, but using different notation. Now, you've already noticed that I've gone a long way around my notation. It's been very systematic, very thorough. I could have taken a few shortcuts in here, I'm sure. But I'm going to introduce you to a new set of notation. I'm going to head this with matrix row operations. And to start with, I'm going to rewrite this system of equations in shorthand form, if you like, in terms of a matrix. So I'm going to take my coefficients, 1 minus 3, 2, 1 minus 3, 2, and then the next 2 minus 1, 1. And then the third one is 2, 1, 4. And the equals value, the constant at the end, and I've got 2, 5, minus 3. And this is what's sometimes called an augmented matrix. It's this system of equations represented as a matrix. And now, combining equations is now equivalent to combining rows. So what I'm going to do here is I'm going to leave the first row the same. 1 minus 3, 2, 2. But in my first step over here, I was eliminating an x using equation 1 and 2. That was equivalent over here to taking this second row and subtracting two lots of the first row. So that's what I'm going to do. I'm going to put here, this is going to become the row 2 minus 2 lots of row 1. So I'm going to go 2 minus 2 lots of 1 is 0. That's the equivalent of eliminating x. I've got minus 1 minus 2 lots of minus 3 is going to give me 5. I've got 1 minus 2 lots of 2 is going to give me minus 3. And I've got 5 minus 2 lots of 2 gives me 1. And that's equivalent to this equation here. 5y minus 3z is 1. 5y minus 3z is 1. For the next step, if you recall, I took equation 2 and equation 3, and what did I do with them? I added those together. So in the matrix system, this is equivalent to just going for row 3, add on row 2. Subtract. That was a subtract, wasn't it? I subtracted those. So over here, I'm going to go row 3, subtract row 2. Subtract row 2. So I've got 2 minus 2. I've got 1 minus minus 1 is 2. 2 subtract 2 is 0. 1 subtract minus 1 is 2. 4 subtract 1 is 3. Minus 3 subtract 5 is minus 8. And again, you can see that's the equivalent of this statement here. So in one step of writing, there's a bit of thought going on in there, but it's obviously a much more efficient way of recording what you're doing here. The next step, what did I do? I noticed that the next variable to eliminate was going to be the z by adding these. So again, I write my matrix. My first one stays the same. 1 minus 3, 2, 2. My second one, I'm going to leave the same. 5 minus 3, 1. And in this step, I'm going to now add row 3 and row 2. 0 plus 0 is 0. 5 plus 2 is 7. Minus 3 plus 3 is 0. And 1 minus 8 is minus 7. And this then is at the point where I can interpret this to say 7y is minus 7, y is minus 1, and then I can go on and solve for z and x as I did before. I can go to this second equation, substitute y and find z, and then I can go back up to the top, substitute y and z and find x. So again, I'll leave you to verify that from this system I would get again z is minus 2 and x is 3. It's worth taking a moment or two just to think about the structure of why that worked. If you notice from that last example, I chose to eliminate the x's, which led to getting zeros in these positions in the matrix. There's nothing to say you have to eliminate the x's. You can eliminate the y's or the z's as well. So let's just think for a moment. If I'd have chosen to eliminate the z variables, let's say, those first two steps would have worked towards getting zeros in that position there. And then my last step, I'll leave the first row the same. If I've eliminated the z's, I've now got zeros here. The next step, or the last step, would be then to eliminate either the x or the y variable to get a 0 either here or here. Now, it wouldn't matter which one you got the 0. If you ended up with a matrix of this structure, then quite comfortably you could say y, you could work out the y's from this one. You could then go back and work out the x from this one, and then go back and get the z from the third one. So as long as you end up with a structure whereby you've got zeros in an arrangement like this, and then another 0 like this, then that system you'd be able to solve. Now, there's a little bit of notation uh, that you will be good to be familiar with. Manipulating matrices into this form, there's a thing called echelon form, Echelon form. And in fact, we're talking about row echelon form. And a matrix that is in row echelon form is one that has, for this size system of equations, where I've got 3 by 3 system, echelon form would be whereby you have the zeros in a triangular arrangement there. And there's actually a function on your calculator that will take a matrix and put it into echelon form for you. Once the matrix is in echelon form, of course, you can then solve this. From here, you'd get the z's. From this row, then you'd be able to work out the y value, and then you go back to the top and work out the x. Now, you'll sometimes see questions then where it says reduce a matrix to echelon form, and it will want this. But just be aware that if you just want to solve the system of equations, which is what you're likely to want to do, then actually any structure that has the appropriate zeros, where you've eliminated the appropriate variables, will work. Okay, now I'd like to look at some of the calculator operations that will do some of this for you. So from just a regular screen, I'm going to go menu. I'm going to go for the 7th option for matrix, and I'm going to create a matrix. So option 1, create a matrix, and I want to enter the augmenting matrix from the start, which had 3 rows and it had 4 columns. Okay, so I'm going to do that, and I go enter in these numbers. So that was 1 minus 3, 2, 2, and it was 2 minus 1, 1, 5, and then 2 and 1, 4 minus 3. And just for ease, I'm going to store that as matrix A, and then I can just refer to it as matrix A. Okay, so let's go menu, into 7 matrix and vector, and you'll see that option 4 here is row echelon form. So I can ask for number 4, row echelon form of, now I can either just pull the matrix from there, or I could have hit matrix A because I've stored it as A, and it will give me the the row echelon form. And notice it's different to the answer that we got, because the row echelon form has fixed it so that I've got zeros in that lower triangular arrangement there, and it's also scaled each equation so that the leading term is 1. So that is what's called row echelon form. I could use this now. Look at this, I can see that z is equal to minus 2, which matched my answer from before. I could use that then to go and calculate y, and then go and calculate x. So the calculator is programmed with a row echelon form function. But more than that, you might have noticed, let's go back to the matrix menu again, and then actually another step would reduced row echelon form. Let's take a look at what that does. Number 5, reduced row echelon form. I'm going to go of matrix A and see what it gives me now. It actually goes a step further. It takes the row echelon form and it goes back and it calculates each of the variables for you. So I can see that z was minus 2, I can see y was minus 1, and x was 3. So it's another way of getting the solution to that system of equations from the calculator. So this doesn't do anything that you can't do in the numerical solution of a system of equations, but you start to see the links between matrix algebra and systems of equations.